This is VLSI data conversion circuits, lecture 25. In the last class, what we learnt was how one would systematically design an NTF so as to achieve the desired signal to noise ratio in the signal band. Of course, as we saw last time, it involves iterating on order, the out of band gain, often abbreviated by OBG, and what was fixed was the signal bandwidth, which is determined by the OSR, and the number of levels of the quantizer, right. So, these are assumed to be fixed and we iterate on the order and the out of band gain in order to achieve the desired SQNR in band, all right. So, clearly the choice of n is still something that we need to discuss a little bit more about. As we saw last time, increasing n only increases the in band SQNR for a given NTF by 6 dB. So, we can take it the other way around and say reducing n by a factor of 2, which means you reduce the number of levels you have by a factor of 2, which will only reduce the SNR by 6 dB, and that can be easily fixed by doing what? Simply increasing the out of band gain. You understand? I mean 6 dB seems like such a small number now, right. By simply increasing the out of band gain by a little bit, the in band NTF can go down a lot, all right, and therefore it is seems very straightforward to gain that 6 dB back, all right. So, then we say okay, we reduce the number of levels by a factor of 2, increase the out of band gain a little bit and get back the SNR. Then you get greedy and say reduce the number of levels again by a factor of 2, right, and increase the out of band gain a little more, and I will get another. So, I mean what have I achieved by going on reducing the number of levels? The design of the quantizer becomes easier, right, because the presumably what we need to do is to compare the output of the loop filter against a bunch of levels and generate an output analog quantity which is which is dependent on these levels, right, and the number of the fewer the number of levels we have, the easier the design of the quantizer inside the loop becomes. So, there seems to be a big motivation to try and reduce the number of levels as possible, right. In the limit, how can how low can you keep going, right. So, you can the lowest you can go is to have 2 levels, right. 2 levels correspond to 1 bit. So, in the limit n can be made as low as 2 levels, okay. So, as you keep reducing the number of levels, what do you expect to happen to the MSA? Goes on reducing, all right, and when in the limit, when you make n equal to 2, the number of levels reduce, the maximum stable amplitude also goes down, and the smallest number of levels one can have is to have 2 bits, I mean 2 levels, or a what is called a single bit quantizer, or a 1-bit quantizer. Okay. The implementation of the quantizer is now as simple as it can get, you understand, and indeed this is done in many practical situations simply because the ease with which the quantizer can be implemented. The question now is, we derived all the models and the math assuming that the quantization noises can be modeled as an additive process with wide spectrum and all this stuff, and as we have seen in the assignment, this is only valid as the number of levels in the quantizer start to become large. So clearly, I mean, we are pushing this too much when we say, okay, now I am going to make the quantizer a single bit one, okay, and then expect all the math and the results to hold. Okay. So it turns out that for a single bit modulator, while the general ideas that we talked about are valid, where noise is still shaped out, okay, but since you are having only 2 levels, okay, I mean technically speaking the quantizer is always overloaded, right, because it is always saturating. Okay. So you find that, and there is no staircase to speak of, right, you just have to jump from the ground floor to the upper level, right, there is no clean staircase. So this linear approximation is, anything is a good approximation to a step, right. For example, if you had something like this, it is now open to question whether the best straight line that approximates, please note that this extends all the way from minus infinity to infinity, correct. So it is open to question whether the best straight line that approximates this is this or this or what, understand. So it is very difficult to define the gain of the quantizer, because the quantizer seems to be perpetually overloaded, correct, and therefore all the nice assumptions we make about additive noise and all that are not valid anymore, okay. But quite dramatically and quite almost by magic, you can still use a single bit quantizer and get away with it, okay. And it turns out that people did some experiments, or ran some simulation experiments and found that the noise transfer function gain must be less than or equal to 1.5, right. So this is an empirical rule, right, often called Lee's rule. Okay, there is a master's thesis at MIT like maybe 20 years back or something like that. Okay. So where a whole bunch of simulations were run on single bit modulators, and a rule of thumb is to say, okay, if I choose an out of band gain of about 1.5, in other words, if I do not make the noise transfer function too aggressive, that makes sense intuitively, right. As you go on increasing the out of band gain, right, a modulator becomes unstable, right, or for a given out of band gain, if I go on reducing the number of levels, the modulator will tend to become unstable, and for a single bit modulator, it turns out that the maximum gain that one can choose, right, as a thumb rule is about 1.5. Now this does not mean that if I choose 1.51, the modulator will magically become, will not work, right. It is just that this is a good rule of thumb. You can always go a little bit above or below this, and as I said, this is an empirical rule called Lee's rule, and works quite well in practice. So, if from the point of view of implementation of the quantizer you decide to do a single bit quantizer, then you choose, you start off, I mean there is no iterating, right. You have the order, you have the order band gain, you choose Butterworth or you know a Butterworth with a passband with complex zeros, right. You compute the in-band SQ and R, alright. It either meets your spec or it does not meet your spec, and if it meets your spec you are done. If it does not meet your spec, the only thing you can do is increase. No, you can't increase the order band gain anymore, because you know at least empirically you know increasing the order band gain does not help you. So, the only thing you can do is increase order or increase the oversampling ratio, because you know the signal bandwidth is fixed. If you want to keep the same order, but you want a lower in-band quantization noise ratio, you simply increase the OSR. You understand? So, this I mean, so therefore, modulators are of two kinds, those with many levels or what are called multi-bit delta sigma modulators, or single bit modulators, and this is where oversampling and noise shaping are pushed to the extreme, right. So, you can take a 1 bit quantizer and make it look like a, within a signal band you can make it look like a very precise quantizer, okay. So, in most or a lot of your PC sound cards, for example, where voice is digitized and you are getting sound out, okay, single bit modulators are at work. So, you can get very high precision and performance by taking a quantizer which is as bad as a 2 level quantizer and putting it in a negative feedback loop and making it really very precise, okay. Now, so let us try and see what are the motivations for going to single bit, apart from the fact that the quantizer implementation is simple, you understand. So, when you try and build a multi-bit quantizer, the loop quantizer is when you try and build a multi-bit delta sigma modulator, the loop quantizer is a staircase like transfer curve, okay. But when you try and realize something like this, you know that in practice you will never get the ideal staircase, right. What do you expect? I mean, okay, offset, there will be offset and there will be gain error and there will be DNL IN, alright. So, let us see what happens when the staircase is not a real staircase, okay, or rather not an ideal staircase, okay. So, please recall again before we go into the nitty-gritty of this, is that the quantizer is a cascade of the A to D and a D to A converter. All right. So, the actual modulator will in practice look like this, for example. All right. So, if the A to D converter thresholds are ideal and the D to A converter, what is the D to A converter doing? It is taking a digital word in and putting an analog quantity out, right. So, there could be errors. I mean, the reason why this quantizer is not behaving properly is because there are errors in the A to D. What errors could be there in the A to D? The thresholds of the A to D converter are not the ideal thresholds, right, and the D to A converter is not ideal, means what? I mean, what is the D to A converter doing? Let us say you had a say a 2-bit word and you want to convert it into an analog quantity. What will you do? The output voltage or current should be B naught times some Vref plus B1 times, or let me call this not Vref but delta, plus B1 times 2 delta. So, if B naught and B1 take on values 0 and 1, you get 0, delta, 2 delta or 3 delta. Okay. So, if the D to A converter is not ideal, it means that the what you get will be not B naught into delta plus B1 into 2 delta. This will nominally be delta and this will nominally be 2 delta, but there will be some errors. You understand? In other words, for an ideal DAC, in this example, depending on the bit code, if the code is 0, 1, 2 or 3, you must ideally get 0, 1, 2 and 3 times delta, correct. So, this is the ideal. What do you think will happen in practice? So, instead of this being, these levels will be off. Please note that the x axis cannot change, that is only code, correct. Only the output levels will be off from the ideal values. Is this clear? Similarly, So, how can you model the error? Can you suggest a way of modeling this error? Pardon? Yeah, okay. So, what he is suggesting is that you can think of a non-ideal D to A converter where the levels are not what you expected, right, as an ideal D to A converter plus some error sequence EDAC, right, where clearly this EDAC depends on code. So, this is a code dependent error, all right, and please note that this is a deterministic quantity and can be determined in principle by applying the various codes to the input of the DAC, measuring the outputs, and you know what the ideal output should be, right, and by subtraction you will be able to get EDAC of n. When we go deep into DAC design, we will understand why these errors come about, but for the time being all that we are interested in doing is studying the effect of non-idealities in the A to D and the D to A converter. The cascade of the A to D and D to A converter form the quantizer, correct. So, the A to D converter will be non-ideal and the D to A converter will be non-ideal. Non-idealities in the D to A converter can be modeled by a sequence which adds to the output of an otherwise ideal DAC, and this sequence is a function of the input sequence into the DAC. Is this clear? Okay. Now, what do you think could be a problem with an A to D converter? What kinds of non-idealities? We have seen this before. So, basically the thresholds are not what you expected them to be, correct. So, an A to D converter basically has a transfer curve like this. Ideally, you should get so this code on the y axis is the code that must be 0, 1, 2 and 3, and this must be input by delta. So, this must be ideally 1, 2, 3. Unfortunately, because of the way an A to D converter is implemented, the thresholds are different from the ideal values and say are perhaps like this. So, the red one is the non-ideal one and the black one corresponds to the ideal characteristic. Yeah, so this is like adding an offset. Yeah. All right. Okay. Now, when you cascade the A to D and D to A converter together, ideally you are expecting a characteristic which was doing this, correct. Now, what do you think will happen? When the A to D converter is not ideal and the D to A converter is not ideal, what do you think will happen? What happens to the transfer curve? Pardon? The y levels will be different, and that is coming because the DAC is not ideal, yes. X thresholds will be different because ADC, very good. So, the real one will probably be like this. Okay. So, this is real and this is ideal. And just as how we modeled the error in the D to A converter, one can also model the error in the A to D converter by, we can add an error sequence here at the input of an otherwise ideal ADC. Is this right? I mean, it is only a matter of what I must add to make the thresholds move. Okay. So, now let us see what the effect of these errors. Please mind you, these are all deterministic errors, there is nothing random about this. Once you make a DAC, you can actually go and find the errors in the threshold of the output levels of the DAC. You can also find the errors in the thresholds of the ADC, right. Now, we would like to understand what happens in the light of these inevitable errors in practice. Okay. And please note that these errors have got nothing to do with quantization. Even if the ADC and the DAC were ideal, you will still have quantization errors. These errors sequences are in addition to quantization, right. So, the effect of these errors therefore is to this is EADC, EDAC. Again, this is Y, this is V. Pardon? The final sequence that you are taking out into the decimation filter is the output of the A to D converter. Isn't it? The final quantity of interest is, please notice that this is the digital sequence which goes into the decimation filter, right. So, this is the digital sequence. Okay. All right. So, in other words, you can say that if the D to A converter was ideal, this V, this digital sequence which goes here is a digital representation of V, right. But unfortunately, the D to A converter is not ideal and the non-ideality is being modeled by the sequence EDAC, which again I will remind you is a function of the code. All right. Similarly, the thresholds of the A to D converter are not ideal, and you can therefore think of this as some kind of error waveform which is a function of the input, right. Okay. All right. So, we would like to understand what happens to our delta sigma loop with these errors in practice. All right. So, let us start with the ADC error first. What do you think will happen, or what is the influence of EADC on the in-band SQNR? Any other comments? Yes? Pardon? Why? Well, what do you think will happen? Pardon?
It is in forward loop EADC.
Yes.
So 1 by 1 plus L of Z.
Correct.
EADC will decrease.
Right. So, great. So, you can see that in any case, I mean you can think about it this way, the output of the loop filter is being quantized, right. So, we are anyway going to add a lot of quantization noise to the output of the loop filter. So, in principle corrupting the thresholds by a little bit should in principle not matter too much. Another way of thinking about it is that the quantization noise is also being added at the same point. Therefore, the transfer function from EADC to the output is the same as the transfer function from the quantization noise to the output, which is the same as the noise transfer function of the loop, right. Therefore, this errors in the thresholds of the A to D converter will get shaped out of the loop bandwidth, or rather out of the signal band, just like quantization noise, right. So, EADC is a benign thing, or let me say EADC, if it is much smaller than the quantization noise, is a benign thing, right, as it gets noise shaped. By the same token, can you now comment on what would happen to EDAC? What is the transfer function from EDAC to the output? Is the same as the signal transfer function, because it's adding, you can think of it as adding directly to the input, right. So, EDAC causes right. Recall that in the signal band you want to make the STF equal to 1. So, errors in the DAC levels appear as if they are added along with the input, okay, and therefore will appear at the output of the modulator as is, okay. I mean this is with the in line with the general intuition that if you have a feedback system, the output is largely determined by the feedback block, isn't it? If the feedback block is creating mischief, then that will reflect in the output, right. And whatever happens in the feed forward amplifier, as long as the gain of the amplifier is sufficiently large, right, all that stuff is I mean does not affect the output of the loop. That is general intuition from negative feedback theory, and these conclusions must therefore come as no real surprise, right. So, one of the penalties of using a multi-bit DAC or a multi-bit quantizer inside the loop is to add this error E DAC, alright, which as I said is a nonlinear function of the input sequence. Okay. So, if you take, and what is this sequence nominally? What is the signal there? It is input plus shaped noise, right. So, the spectrum here consists of the input plus some shaped noise, right, and E DAC is a nonlinear function of this sequence which has got this spectrum, right. If you take something like this and pass it through a nonlinearity, what do you expect you will get? If you take a sinusoid and pass it through, you will get harmonics, very good. So, you will start to see harmonics of the signal, and what else do you think you will see? What about noise? So, you pass it through a nonlinear transfer curve, and stuff from, I mean you please recall that if you have two sinusoids at omega 1 and omega 2 and pass them through say even a third order nonlinearity, you will get components at omega 1 minus omega 2 and omega 1 plus omega 2, this is for second order nonlinearity, you will get 2 omega 1 minus omega 2, 2 omega 2 minus omega 1, 2 omega 1 plus omega 2, 2 omega 2 plus omega 1, and therefore, it means that noise from, for example, omega 1 minus omega 2. So, consider a noise component here and a noise component here. Once you pass them through a second order nonlinearity, what will happen is that it will cause the in-band noise to fill up, alright. So, now we are stuck with not only having harmonics of various magnitudes because of nonlinearity folding causing harmonic distortion, right. This quantization noise will also fold back into the signal band due to these nonlinearities. Does it make sense? And therefore, what has happened now? I mean all the hard work that you put in to try and shape the noise out of the signal band has been brought to naught simply because of errors in the output levels of the D to A converter. Does it make sense? Okay. So, how, I mean what do you think we can do to fix should be done to fix this problem? So, I mean the only way to fix this problem is to make sure that the DAC, even though the number of levels in the DAC are small, you must make sure that those levels are sitting on a perfect straight line, right. Right now that is not happening, Okay. So, ideally if I join the midpoints of the staircase, I must get a straight line. Now, what is happening? It is I am getting some kind of weird nonlinear curve, right. So, it is doing something like that. Is this clear? So, linearity, the bottom line therefore is that linearity of the feedback DAC is very, very important. Because the errors in the DAC output directly it appear as if they are being added to the input and therefore appear directly at the output of the modulator, whereas errors in the flash I mean in the A to D converter thresholds are not really a problem because they get noise shaped. Is this clear? Okay. So, this is regarding a multi-bit modulator. So, now if we change the scene and make I mean do a similar analysis for a single bit modulator, what do you think will happen? An ideal single bit quantizer's transfer curve must look say like this. What do you think will happen if you have a non-ideal single bit quantizer? I mean you have a single bit A to D and a single bit D to A, right. So, the ADC threshold not being correct means that there will be the staircase will shift horizontally, okay, and the D to A converter not being ideal means that the levels are not the same as the ideal ones. Okay. So, how can this be modeled? In the same way, but given that there is only two levels in the D to A converter output and there is only one transition point, the ADC error can be modeled simply as a offset, right, and the D to A converter, this is a 1 bit ADC and the D to A converter error can be modeled as, instead of getting say 0 and delta, I am getting alpha and delta plus beta. So, what can this be modeled as? Offset and gain error. Between any 2 points you can draw a straight line, right. That straight line may not have a slope of 1 and will not pass through the origin, but it is a straight line nevertheless. So, you have the D to A and then you can model it as an offset and a gain error. So, let me call this G1 and then add an offset. All right. So, now if we analyze what happens to a single bit modulator, there is an offset in the ADC there is say a gain error G, which is very close to 1, because hopefully these errors are small, and there will be a V offset in the DAC. So, what do we conclude? The offset of the ADC is as usual not a problem at all. The offset of the DAC, do you think it is a problem? It will simply add, it will appear as if the input is offset by some amount. So, as far as linearity of the entire modulator is concerned, again it is not a problem at all, simply because as we discussed early on in this course, if you have an offset is benign, because in a system you can always remove it by estimating it and correcting it off. What about the gain error here? What do you think it does? The feedback gain changing slightly will only introduce a gain error in the overall transfer function. Again, it does not affect linearity. You understand? So, this is an extremely important advantage when you design a single bit modulator, right. So, in a single bit DSM, right, the D to A and A to D errors do not matter. Because they just translate into gain and offset errors, okay. And the intuitive reasoning for this is that if the DAC errors, which are the usual cause of the problem, are not the ideal ones, they can simply be modeled by, I mean, if you have 2 points, you can always draw a straight line, right. So, the errors in the DAC levels will only result in an offset and a gain error, which are very small. So, one need not worry about trying to build a good D to A converter, where the levels are very precise. That is something we need to do when you use a multi-bit quantizer. So, you can see that the multi-bit quantizer has some advantages. One is that you can use an aggressive noise transfer function, okay, and because the out of band gain can be high, all right, and therefore you can reduce the in band quantization noise, all right. Or if you want to realize a given SQNR within a given signal bandwidth, the OSR can be reduced, all right. On the other hand, you need to take a lot of care to make sure that the levels of the D to A converter are very precise. On the other hand, a single bit design, the quantizer design is easy, one need not worry about the linearity of the DAC itself, but the out of band gain can only be about 1.5, and if you want to get a high SQNR, this translates to either increasing the order or increasing the OSR, which is mostly what happens in practice. You understand? Okay, we stop, we will continue in the next class on